this video, we're going to talk about molecular shapes, Lewis structures, geometries, bond angles, intermolecular forces, and essentially what you need to know condensed into a few minutes. So these are the elements on the periodic table, as you all know, and where they are on the periodic table is dependent on their electron configuration, and that determines how many bonds they like to form, essentially. So you can think of noble gases as wanting to have no friends, sad life, but that's what they are, no bonds. The halogen gang, they like to form one bond. Oxygen's group likes to form 2, nitrogen's 3, and then carbon's group 4. And you'll pretty much always see carbon with 4 bonds. Hydrogen can only form one bond because it only has one orbital and one electron with which to share. So you can think of it like this. If the atoms have as many bonds as we just said, we consider them essentially neutral. If they have more bonds than they want to have and they're following the octet rule, you can consider them to be positive. And if they have less, that means they have an additional electron paired up, and therefore they would have a negative charge. So when you're looking at a Lewis structure, you can kind of follow those rules. So if carbon has 4 bonds on it, it's good. If nitrogen has 3, it would be neutral. If you see like ammonium, which has NH4, it's going to have a positive charge. Oxygen will typically have 2 bonds to it. If it only has 1, it's going to have a negative charge. And the halogens will typically just have 1. So looking at the shapes, this is a lonely atom. This doesn't really have a shape. But if I bond another atom to it, the only possible shape that could be is linear. Now, whether it's going to be polar or not depends on the difference in electronegativities between the atoms. So if you have 2 of the same element, like one of the Brinkelhoffs, then it's obviously going to be nonpolar. There's no difference in strength, and the bond angle is kind of just 180. You can also have linear molecules with 2 atoms bonded, and if there are no unshared pairs, this is the shape you'll end up with, nice and linear. So this can either be polar or nonpolar. It all depends on the symmetry of electron distribution. So if you have like carbon dioxide where there's carbon in the middle, 2 oxygens on the outside, oxygen being the second most electronegative element, you'd say should be polar. However, because their poles are equal in opposite directions, they're going to essentially negate each other and result in a nonpolar molecule. If you had something like hydrogen cyanide, you have HCN, you have a difference in strength that leads in a dipole towards the nitrogen, which is the more electronegative element. So either one of those, if it has 1 atom bonded or 2 atoms bonded and no unshared pairs in the central atom, you are looking at a linear structure. Now, if I add another atom, right here we have trigonal planar, and you can figure out that if you took a pizza and you cut it in 3 pieces, you'd be looking at a bond angle of about 120. This can be polar or nonpolar, but again, it all depends on symmetry. If you have 3 of the same atoms bonded off the central atom, then it's going to have to be nonpolar. If you have, 2 H's and an F, well, you're going to have a difference in strength, and you're going to have a net dipole towards the more electronegative element. So those are the 2 shapes that we can look at in 2 dimensions and accurately predict what they look like. The next few molecules are going to start off with, you have to look at them in 3 dimensions. So this right here would be a tetrahedral shape. So carbon with all single bonds is pretty much just going to form this shape right here. You think with 4 things sticking off of it, based off what you just saw, it should have a bond angle of 90. Not true. In 3 dimensions, it's going to spread out so that the bond angles are 109.5 degrees. Right? And again, this can either be symmetrical, so if it's like methane, which is just CH4, you have 4 equal strength things off of it, you're going to have a symmetrical molecule that is nonpolar. However, if you have like 3 hydrogens and again like a fluorine or chlorine or some other electronegative element, you're going to end up with a bond polarity there, and you're going to have a net dipole towards the more electronegative one. So when we're determining polarity, there's 2 possibilities that always lead to something being polar. That's if it's asymmetrical, it's going to be polar, or if you have an unshared pair of electrons on it, that by default makes it asymmetrical, and you're going to end up with a polar molecule. So the molecules I've shown so far can go either way. The ones that I'm going to show you now are polar pretty much by default because of their arrangement of electrons. So this is tetrahedral. Now if I remove one of those single bonds and I replace it with an unshared pair of electrons, you have a molecule here like ammonia, NH3, where it's going to be polar. You have an asymmetry based on that unshared pair of electrons. Now, the bond angles here aren't really going to be 109.5. You would expect that this unshared pair is going to sit a little bit flatter to that central atom and therefore cause more repulsion, pushing the other bonds closer together. You'd really end up with something like 107.3, depending on what these other atoms are. But just you need to know that it's a little bit less than 109.5. This is always going to be polar. Then, if I remove another atom bonded and add another unshared pair, well, now we have something that looks like water. And again, water is going to be polar. As long as you have different strength atoms, you're going to have a net dipole. And this right here, because it has the two unshared pairs, you would expect those to sit a little bit flatter. You're going to have a smaller bond angle than 109.5. You really actually, with water, in fact, you have a 104.5 bond angle. So we talked about molecules being polar or nonpolar. Now we're going to just get into a little bit about what that impacts. So intermolecular forces, which are the forces of attraction that exist between two different molecules, can range from London dispersion forces, which are the weakest for a comparably sized molecule, and that happens with two nonpolar molecules. It's just based on the general temporary lopsidedness of electrons in the molecule. Then we have dipole-dipole interactions, which result between all polar molecules. When you have a polar molecule, you have a partially positive end, partially negative end, and that's going to attract to the opposite polarities on a neighboring molecule. Then you can also have hydrogen bonding, which is like super duper dipole-dipole, like what you observe in water, where you have either a nitrogen or an oxygen or a fluorine directly bonded to a hydrogen. That results in an extreme polarity, where you also have an available unshared pair of electrons that can really accept a positive charge. So there we go.